Hey guys, welcome back. This is Frank, and welcome to our IGCSE Cosi Chemistry revision videos. Our current unit is C6 rates. So we're starting a new unit today, and this unit is mainly going to be about rates of reaction. So how what they are, how we measure them, and the determinants. So what determines like the rate of reaction, and we also have some other stuff, including the composition of air. How to make nitrogen fertilizers. So like the industry process called Haber process, and how to make sulfuric acid. So the industry process called contact process. So yeah, it's a unit. I think that because the main concept about rates is quite simple to understand. So I guess it's mainly about about the stuff that they just want to put in here. But whatever. That's fine. We're gonna start by looking at uh how what rates of reactions are and methods for measuring them. So rates of reaction, well, as the name suggests, is basically how fast chemical reactions go. So because we know rate, when we see rate, it's about dividing by time. For example, speed is the rate of change in speed. The rate of change in distance, and acceleration is the rate of change in speed. So the rate of reaction is just really how fast uh, the reactions are going. And we have two main ways of measuring them. One, we can measure how much products it produces after a certain amount of time, so maybe 30 seconds or a minute. And we can also do it the other way around. We can also limit the a certain amount of reagent or product and test how much time it takes. So maybe to produce 30 decimeters cubed of this gas, or maybe the amount of reagent. So maybe by using 50 grams of I don't know of magnesium or whatever, and we measure the time it takes to use a timer. So it would be very obvious which one of these is which, because for how much products we usually use like a um, measuring kind of equipment. So maybe like a measuring cylinder, because it's measuring cylinder, you measure it. And for how much time it takes, you usually have a timer. So today, I'd say yeah, depends on what we want to measure. We can have different methods for measuring them. So let's take a look at some of these methods. So I've already found the pictures here. So let's take a look at the first one. The time taken before a cross disappears. So basically, this would work with any reactions with solid precipitate, especially like well, it can be soluble, because otherwise it can't be a precipitate. But like if you have an insoluble in precipitate, and preferably has a color like it's not transparent apparently, but if it's transparent, it's not precipitate. But yeah, whatever. It would turn the if it would turn the solution cloudy. What we could do is uh put a cross at the bottom of a glass beaker, so you can see through it, and then you add whatever you want to add in there, and you measure the time it takes before you can like the cross is completely covered by the precipitate. So a very simple concept. Here I think they're using some hydrochloric acid and sodium sulfuric. So yeah, sodium sulfate. That is not sodium sulfate, but yeah, something that would generate sulfur um sulfur solid. So it's sodium thiosulfate solution with a dilute hydrochloric acid. It will give you a solid sulfate sulfur precipitate, and sulfur dioxide gas, and as well as hydrogen. Yeah, as well as sodium chloride and water as a liquid. But whatever. Basically, you would have different, maybe maybe different uh, uh, different concentration. That was the word. Sorry. So you have different concentration of this sodium uh, thiosulfate solution, and yeah, you might be able to see here. It has 50 plus 0, 40 plus 10, 30 plus 20, and so on and so on. And yeah, basically it times, I suppose it's maybe 30 seconds or whatever. And yeah, so basically the time it takes to kind of uh, so that the cross on the bottom is no longer visible. So here you can read it takes uh 32 seconds, 35 seconds, 47 seconds, 1 minute and 14 seconds, and 3 minutes and 48 seconds, and it's still kind of not really so like yellow, because yellow is the color of the sulfur precipitate that is generated. So yeah, basically measure the time it takes, and of course from this it will be very direct. Oops, it will be very direct to tell that this reaction happened at the fastest rate, and this the one on the right at the slowest rate. So because it takes longer time. So yeah, that's for time taken before cross disappears. However, this is a very I'd say subjective kind of method, and very inaccurate method, because well how to exactly define when a cross disappear, right? Like you could say it has disappeared, but your peer might say no. Maybe we're still able to see it a little bit, maybe so it's really not really accurate. So uh, it's not really recommended, but yeah, it's very useful if you have a reaction with solid precipitate, and it gives you a general idea, especially if the time taken varies a lot when you vary the concentration. So yeah, the next one is displacement of water. So this would work with any reactions with insoluble gas products, because apparently you're going to bubble it through water, and if it's soluble, like carbon dioxide, I don't know, you're probably going to get aqueous carbon dioxide, which is no use. So yeah, basically how it works is that you would have something producing gas over here, and then it will come through this tube into the beaker or the measuring cylinder of your choice. I would say in the actual experiment we should use measuring cylinder, because it will tell you very directly how much exactly gas has been produced. But then it bubbles up, and because the gas takes up a volume, it will kind of squeeze down on the oops. It will kind of squeeze down on the water, and then the water will be pushed out into the sink. So yeah, that's why you can measure the amount of gas. So usually with a measuring cylinder too, you would kind of turn the other way around. Well, of course you're gonna turn it the other way around, but then maybe it will start at 100 or something, and you read backwards, but whatever. And then here you have a beehive shelf. So in order to secure this tube so that it doesn't like just flow away, you would have what we call a beehive shelf. So it looks kind of like a beehive, kind of, maybe. But anyway, you have a little hole on the bottom, and you can put the tube through, and then on the top it goes out, so that it will become something that you see over here. So this is actually a very abstract diagram, because the tube kind of magically goes down, and then this speaker kind of magically floats in the water. But in reality, it would look more something more like you have a beehive shelf, and then you have a little hole on the bottom, have a little hole on the top, and then it goes in, and then it goes out, and then the beaker is just gonna cover the entire bottom. So it's gonna look something like that. So that's gonna be the bottom. But anyway, moving on. This is our displacement of water method, so it works with any reactions with insoluble gas products. And it's rather accurate, because if you use a measuring cylinder, you would get exactly how much gas has been produced. But yeah, we're going to talk about more accurate method, which is a gas syringe. So it would work with any gas products, so that's good. You can do carbon dioxide with it even, and it is very preferred because a gas syringe is usually very accurate, and you wouldn't need to worry about some gas that are slightly soluble, which makes things more complicated. But for this one, basically how it works is that the gas that is being produced comes here, goes up the syringe. Oh, I mean up this tube, and then over here and into the syringe. And Well, I hope you guys have all seen the syringe before. So basically, similar to the displacement of water, it would push the plunger out so that there are some readings on this glass tube, uh, and then you would be able to see how much gas is being produced. So maybe after some time, there's only like one, two, three, so maybe three kind of I can't tell the unit, but like 3 unit. And then for here, it's almost all the way, so you can see very clearly the difference. So that's also a very good way. And on the actual gas syringe, it would have the units in centimeter squared, or I mean centimeter cubed or decimeter cubed or whatever. So a standard unit. So we'll be able to actually read from it, and similar to the measuring cylinder, but even more accurate. So this is a preferred method, and of course you can have like a loss of mass. Loss of mass. So basically, how you set up this experiment is that you have a stopwatch, of course, as always, and then you would put some some liquid inside, and then you would tear it on the balance, so that you would see, or you could not tear it and just read and then just subtract. But I find it harder. It's less intuitive. But then you put in the reactants, you tear, and then you put a cotton wool on the top. Because this is very important, because if you don't put a cotton wool on the top, if you just leave it open like that, the water might come out and splash, and especially if you have acid inside that flask, you might not want that on your body. So a good idea to block it with a cotton wool, so that only gas can escape. So as I've said, this works with reactions with gas products. So if I have a gas product and it's gonna escape from the cotton wool, so the mass of the overall thing would decrease. And because reagents are used up, and then the reactions are used up, and then the product would leave the system. So there will be a decrease in mass, and that decrease in mass is basically tells you how much gas it produced. So yeah, remember to always block it with a cotton wool. This is very important, because otherwise you're gonna get splashed. And then yeah, that's it for today's methods. So just a quick recap: we talked about time taken before cross disappears, works with solid precipitate. This displacement of water works with insoluble gas products. Gas syringe works with any gas and is preferred, and also there's loss of mass. In the next video, I hope I will talk a little bit about the determinants, so what determines the rate of a reaction. So stay tuned, and I'll see you guys in the next video. Bye!